Morning, everyone. Just to start us doing some review for our final, hopefully you can access our summary notes. I'll leave a link on the Google Doc that we have so far. I'm hoping to go over some of the major concepts from each of the chapter, lesson by lesson. If you do have any questions, do feel free just to ask one another and also ask myself as well. But hopefully this will serve as a good review, just a summary of the 2 years that we've gone over, and we'll go from there. The lesson for today here, we're just going to summarize some of the measurement techniques that we saw based on your textbook. Some of the textbooks have this in chapter 11. Some of them have it separated the additional higher level stuff in chapter 21. But again, we're just going to highlight some of the major features in each of the chapters. One thing these summary notes don't have are actually practice questions. So hopefully my thought is you can just watch the lesson. We can overview some of the major topics from each of these lessons. I know for a lot of this grade 11 stuff here, this was semester 1 for some of you guys, but we're just going to have a look together. I'm going to overview some of the main topics. We're going to throw out to a few questions here and there, and I'll try to supplement it with some questions that you can be practicing. Definitely, you can feel free to study beyond, sort of at a quicker pace than we're doing here, but at least I didn't want to overload you, so I'm going to try out to do one review lesson per topic. So with that said, we're going to do chapter 11 on measurement. We started off here the course talking about depending on what I was measuring, we saw that we can have different prefixes. So I have a quick picture here of the prefixes here. We really only started from giga, which is 10 to the 9, all the way down to the nanos or the picos. Let's say atomic radius was times 10 to the negative 12. It's nice to be able to memorize some of these prefixes. These puts me in the right power of 10. Our base unit, which is our SI unit, we saw here has no prefix. That's going to be our, in physics they call them MKS units, because for length we use meters. For mass it's better to say kilograms, albeit in chemistry kilograms of chemical is actually quite a lot. We typically use grams. If you think about molar mass, you think about the balances that we have in class, diagrams or electronic balances, everything has been grams, so grams was fine for us. The SI unit for time was a second, so that ends off the MKS units from physics. We can get longer than seconds, like minutes. When we did reaction rates, we did how many degrees Celsius did it change per minute, or how many grams did we get per hour. We had that as a time unit. For a temperature unit, it's always best to use our absolute scale. Temperature is going to be somehow linked to the average kinetic energy of particles. And because kinetic energy is a scalar, we want scalars to be positive values. I don't want to suddenly have temperatures that drop below 0 and suddenly be negative. So when we switch over from the Celsius to the Kelvin scale or the absolute scale, at least the Kelvin gives us all positive values. At least we have this link a little bit stronger tied. One of the main concepts in chapter in grade 11 was measuring amounts of chemical. We basically started pre-boxing chemicals. Nobody has the time to actually count 1, 2, 3, 4, actually counting individual particles. When you go to the store and you want to deal with this chemical, they already are pre-boxed for you in packages called moles. And we saw in chapter 1, that inside every box or inside every mole was an Avogadro number of particles. So mole itself actually is itself an SI unit. If you're going to shorthand the word mole, just MOLE or MOL. Careful when you're using the word, let's say, molecule. If you're going to shorten the word molecule, I wouldn't make it any shorter than, let's say, MOLEC. So molecule, my student teacher used to like saying MLC, that's fine. But if you start dropping that C, it starts looking like mole as well. So just careful with your notation there. Those are our standard base units. We actually have 2 others. I think in physics we do current and we do luminosity as well, but at least for chemistry's sake here, these are the 5 that we care about. Surprisingly, for the SI units, this is actually a fairly short list. Whether we do the 5 or the 7 in total SI units, what about all the other quantities? What about things like area or density or speed? What about all those things I like measuring? What you're going to see is those ones there are actually going to be a combination of some of these SI units. So for example, if I wanted to do area, say I was doing area of a rectangle, I want to go length times width. The length I have the SI unit for. We're going to use the standard unit meter. Width, we're also going to use meter for it. If I combine them, if I multiply that by itself, then suddenly area has what's called the derived unit. It's not a new SI unit, but it's just a combination of meters times itself, and suddenly we have something like meters squared. Let's do density as an example. So density, we know has a formula mass divided by volume. It measures how packed away something is. Now mass, we have our SI unit. Again, in say physics or biology, it's better to say kilograms. For us, we're just going to use grams on top because we're doing it in chemistry. For volume, again, just assuming volume is like a length, width, height, that's going to be sort of 3 combinations of distance, and that's going to give you a meter cube. So density here can be quoted gram per meter cube or decimeter cube. And basically, we can keep this SI unit list fairly short, but I can derive it in whatever fashion that you need. Especially when numbers get to be really big or really small, we switch to this guy here called scientific notation. For correct scientific notation, some things you want to look out for here is the first digit has to be between 1 and 9. Okay, so it shouldn't be like 12 times 10 to the 2. It shouldn't be 0.12 times 10 to the 4. Although numerically all 3 of those are the same value. For proper scientific notation, this first one, between 1 and 9, what we do is we separate, because that's between 1 and 9 is not a 12, we sort of separate off the order of magnitude. This part here actually just tells you how large or how small the number is. If I have powers that are bigger than 10, I move the decimal place to the right. If I have negative, I'm just going to move the decimal place to the left-hand side. Your calculators will nicely shorthand this because we use standard scientific notation so much. So your calculators, I can probably type in this number here, 1.2. It'll either show it as an EXP button or an EE button. Make sure you know where that is on the calculator, and all you need is you need to just type the power afterwards. That EE button here is a shorthand for 3 buttons. It's going to type in the times 10 to the power of. It's going to know you're trying to do scientific notation, and it's going to put this 3 here as the power of 10. It's going to move the decimal place as we like. All of our metric prefixes are nice. They're sort of based on the same counting base 10 system that our numbers or digits are based off of. So really works really well with our scientific notation as well. When we start looking at sig figs later on, for proper scientific notation, these numbers here are called base numbers. The numbers on this side, the numbers that are not part of the order of magnitude, those ones here are called the base number, and the base number are all significant. You'd be surprised sometimes on the IB exam, they just ask you, here's a sample measurement, how many sig figs is this number? It should be a gimme, okay? Otherwise, we do need to be practicing through our sig fig rules. We'll see that in a second here. Especially because we have all these prefixes and all these different orders of magnitudes, what we want to be able to do is we want to be able to do some unit conversions. This is the structure for doing a unit conversion. We usually go question mark, whatever unit that we want. We take the number as written, this is the one that we currently have, and we're going to accomplish the conversion by multiplying by a fraction. This fraction here will have the unit that we have currently canceling out in the denominator and leaving you with what you want on top. The nice thing about this sort of setup here is you can tack on as many fractions as you want one by one, and actually as long as all the other units cancel out, we're going to end up with the units that we want. So I'm just going to do a quick example of this one here. Let's say I was interested in converting here. I have 5 liters. I want to convert to decimeter cube. I know some of you already know the answer already, but just humor me for a second. We're just going to try out this conversion. This one here is a little bit strange of a conversion. Most times when we do conversions, our base unit doesn't change. If it's liters on this side, usually I'm expecting it to be meters on this side. In this case here, because both of them are units of volume, we typically use liters a little bit more when we're talking about liquids or solutions. This one here typically refers to, it could be a solid like length, width, height kind of thing, so it's measured in meter cube. Both units are perfectly fine for liquids as well as solids, but it's a little bit strange because we're actually converting from one base unit to the other unit. It's not just changing from one prefix to the other prefix. So what we're going to do here is we're going to set up our structure. Our final unit is supposed to be decimeter cube. I'm going to start off with the number as given, so we have 5 liters. I want to slowly get from liters to decimeter cube. If I knew the relationship liter to dm cube right away, I can just do it this way. In this case here, let's pretend I didn't know this conversion just yet. The conversion that I might know here is 1 milliliter is equivalent to 1 centimeter cube. If I have a box that is 1 centimeter on every side, the amount of volume, the amount of space that that box holds is equivalent to 1 mil worth of liquid. That's actually going to help me convert milliliters over to the meter cube base unit. So that means we need to convert to milliliters first. So liters into milliliters. We can then use this conversion. It's a little weird going through just putting in all the units first. I'm not even worrying about the conversion factors. There's where my true relationship came in. 1 centimeter cube was 1 milliliter. And here, especially when we're trying to convert a power centimeter cube into decimeter cube here, it might be a little bit hard going centimeter cube directly to decimeter cube. What you can do, we saw, was we can actually do the one-dimensional conversion, centimeter to decimeter cube, but we're going to cube the conversion. We're going to do that same conversion 3 times, and overall, the centimeter cube will be canceled out by the 3 orders of centimeters, and we're going to pick up a decimeter cube. So let's have a look here. I tend to like going through to avoid negative exponents. We're going to put a 1 beside the thing that's bigger. I know 1 liter is bigger. In this case here, we had from a relationship 1 and 1. Between decimeters and centimeters, deci is 1 power of 10 bigger than centi, so 1 for the decimeter. Once you put the 1 beside the thing that's bigger, all other powers are now going to be positive. So for example, if you look at milli, milli by itself is supposed to mean 10 to the negative 3. What they're trying to suggest here is they're trying to get you to say 1 milliliter is 10 to the negative 3 liters. I generally find people have more trouble when they deal with these negative powers. So what we've done is for our unitary rate, we put a 1 beside the thing that's bigger. Even if milli would have itself had a negative power, we now need 10 to the positive 3 milliliters. I need 1,000 thousandths of a liter. I need a huge number of a small unit to make one big unit. So this one here would just be plain old 10 to the 3. Similarly with deci to centi, you can convert centi back to the base unit meter and then meters to decimeters if you have to, but we saw on the chart here, they're just off by a power of 10. So 10 centimeters make a decimeter. Eventually you'd end up top numbers you multiply, bottom numbers you divide. We're going to divide it by 10 3 times. So divide 10, divide 10, divide 10. And that in this question actually cancels out. So that reminds us that decimeter cube is actually equivalent to the unit liters. So IB doesn't like using liters all over. You're going to see it switching it to decimeter cube. Just remember to just sort of match it up for yourself. A decimeter cube is a liter. You can leave your answer in liter if you want, but just careful when they word the problem. They're going to quote it in decimeter cube as opposed to liter. So for example, when we did our solution stuff, I may have 1.5 molar solution. In regular Chem 11, Chem 12, we would read that as 1.5 molar or 1.5 moles for every given liter. For IB, what they're going to do is they're going to switch this here. They're going to say 1.5 mole per dm cube, or if I just write it out in one line, 1.5 moles, and then dm to the negative 3. Again, if I have negative, it means per, okay, and that's going to put the unit mole per liter. So that's how we did our unit conversions here. Most of these conversions, which are metric, are definitions, so we don't need to worry about significant figures. Unfortunately, the only number here that is limited by precision are your measurements. So depending on my exact experiment, depending on how good of a ruler I was using or whatever measuring device I was using, we're limited by significant figures. We want to make sure our final answer has the correct significance as represented by the observation. So for significant figures here, they identify digits that have meaning, digits that I'm not going to round off. And surprisingly here, yes, it contains all the certain ones, everything that I'm super sure of, as well as one guess, as well as one estimate. That number might very well be off, but it's okay. It still gives me some meaning. It still gives me some approximation of what the next digit should be. So just quickly here, when we do our significant figures, our conversions for metric prefixes here, those are definitions, or if I deal with counting numbers, we say those ones that are exact. Because they're defined to be that way, they have no uncertainty to it. It's like they have infinite significant figures. So for example, 1 ton is defined to be 1 million grams. That's by definition. So even though when we use our rules later on, the 1 looks like 1 sig fig, this million looks like 1 sig fig, because it is by definition, I force it to equal this way here. These are infinitely precise. The part that we actually get into trouble is with zeros. Sometimes they're important, sometimes they're not important. So instead what we're going to do is we're going to use this what's called the arrow rule to identify when zeros are important, when zeros are not. So I know we did this in class. Let's say we have the number like 500 pizzas. Okay. So we have 500. We know digits between 1 and 9 are significant. So I know this one here is going to be a significant digit. I don't currently know if it's going to be one of the certain ones or one of the guesses. The question here is, are these zeros here going to be significant or not? In this case here for your arrow rule, remember you only get to shoot this arrow once. For numbers that don't have decimals, you shoot left. This number here doesn't have any decimals. The arrow is going to shoot to the left. The rule for this arrow is it can cut through as many zeros as it does. When it runs into something that's not a zero, it gets stopped. The arrow that's cut through the zeros has indicated for you zeros which are called placeholders. They're in some sense here insignificant. They're not giving you any extra meaning. They're just making sure that this 5 here is in the right position. This 5 here is in the hundreds. We have actually ordered 500 pizzas, not 5 pizzas. So in this case here, this is a 1 significant big number. It has the precision of 1. What if I wrote the exact same number like 500.0? In this case here for the arrow rule ends up shooting to the right because it has a decimal. The arrow cuts to the right. It gets stopped by the 5 very shortly. In this case here, everything left over is important. So I have 4 units of meaning. This one here suddenly has 4 sig figs. Based on my sort of meaning and then keeping one guess, I know I'm sure the 5, I'm sure the 0, and the 0. My guess, my eyeballing value is the one at the very end. Numerically, both of these are 500. That didn't change. But based on the way I measured it, based on my device, I have a lot more precision in that number. In general, the more significant figures means more precise. It's actually better to say the more decimal places, the more precise something is. So that's just in a nutshell here, significant figures, especially when we're dealing with rules for significant figures. Make sure you know these 2 rules. When we add and subtract, it's like rounding to least decimal places. When I multiply and divide, it's rounding to the least significant figures. So let me give you an example of this one here. This one shows up a little bit when we do our titrations. So let's say I have a barrette, so it's a long glass tube here. Our barrettes just happen to be 50 ml barrettes. Strangely enough, it has a 0 mark up here and the 50 ml mark down here. Remember, it has that stopcock valve on the bottom. You can slowly open and close it and drop in liquid as you need. Drop the base. What I would generally tell people is just fill this up here something more than half. Let's say you start filling in your solutions. Water does that little meniscus shape here. What you're going to do is you're going to make a reading of what the barrette says right now. We're going to be looking at the bottom of the meniscus, the bottom of that curve there. Let's say for argument's sake here that says 10.00. Remember, this does not mean I filled in the barrette with 10 mils. We know that if 50 is down here, I filled it with some 40, almost 45 milliliters to get it up to this 10 mark. The nice thing about a barrette here is I don't really care how much I initially started pouring in. You're just going to take a reading at the beginning. That's called V initial. After you're done dropping the base or whatever solution you're dropping, this liquid layer would have now dropped. You're going to take a second reading. Let's say for argument's sake here it is 22.34 milliliters. Again, that doesn't mean that there's still 22.34 left, nor does it mean 22 has dropped in. What we're going to end up doing is we're going to end up having to subtract these 2 numbers to find the difference in volume. So let's say we did that here. For titration, typically we want to do a few different trials. So the first trial, my barrette went from 10 to 22.34. I set up for another trial, so this one here still set 22.34. I'm just going to get out my calculator here, 22.34 plus... let's say my barrette then read 34.72. Okay, so starting reading, ending reading. If I realize, oh, I don't have enough solution for the next run here, I would top it up a little bit. So let's say between trial 2 and trial 3, I topped it up. Now it says 15. So be it. Okay, it doesn't matter. The starting reading isn't important. What we really care is the difference. So plus, let's do 12.80. Okay. So let's say I did 3 trials, and those are the readings. None of these numbers are actually implying how much solution there actually is in the barrette or how much I've dropped. We actually need to do the difference, subtract the 2. In this case here, all of these could have uncertainties to them, so 0.05. We do half in the last digit if it's an analog measurement like this. So we do our differences here, 12.34 over here, 34.72 minus 22.34, I'm getting 12.38. And in this case here, just show it to you with the errors. I'm doing a subtraction, but your errors still end up adding as a rule. Errors generally get bigger. So 27.8, big number minus small number. That's one reason why the numbers are upside down. And we're going to get 12.80 plus or minus. If the errors have suddenly got bigger, if we were on the high side of the big number and the low side of this number here, this ends up giving you 0.1. Remember to always do a double check here. We're going to always round our error to 1 sig fig. And then what we're going to match up for is make sure that the guess, in this case here, our significant figure rules here actually lets us keep that second decimal place. But unfortunately, this doesn't line up. In this situation, we're going to actually round this number up to where the error's position is, which is the tenths place. I'm going to rewrite this number as 12.8 plus or minus 0.1. And therefore, my guess of the tenths place will line up with this one. This one could be wrong, 12.9, 12.7, 12.6, and that sort of lines up well with this error region, this sort of confidence on either side. If I were given these readings here for titrations, the whole point of a titration is to be super precise, super close together. It's possible all three numbers are all different from each other. In this case here, I noticed trial 1 and trial 2 are a lot closer together than, say, trial 3. We would actually drop out this third one here. This one perhaps is an outlier, perhaps doesn't follow the trend, so we don't need to average that one in. So in the end, when I do a simple average, I'm just going to average these two. I add them up, divide it by 2, and that puts me right in between, which is 12.36. And then your error will also average in that situation. So just be careful. Sometimes all three numbers are different. Average all three or however many trials. If you are the scientist and you're realizing, wait, these are a lot closer than this one, you are allowed to drop the one that's missing or the one that's far off. Doesn't have to be successive trials. It could be trial 1 and trial 3 are closer together. Maybe drop out trial 2. But the whole point is to be really precise. I could even have told you the concentration roughly what it is. By doing a titration, I want to know more significant figures, more digits for that concentration. So those when there are sig figs, that's how they typically like asking it in paper 1. We switched over to do a little bit of graphing. So graphing is a nice sort of visual look at our trends. Most of our graphs in high school have been straight line fits. As you get into university, don't be surprised if the data looks like it's a curve, then do a best fit that's a curve. We're basically eyeballing values. We're basically saying when I make measurements, there's always chances of me on the high side. There's always chances of me on the bottom side, on the low side. Those ones there are because of random errors. These ones here are random fluctuations, equal chance of being up or low. The whole point of me taking multiple trials is to hopefully minimize if some are overestimates and some are underestimates. I'm hoping to cancel out some of those really high ones, some of those really bottom ones, and hopefully get something in the middle. All the dots that I take down is just to find out this best fit line. Once I find the best fit line, I don't need the dots anymore. So that's going to be your general trend. When you do a scientific experiment, it's always good to do a fair test, which is I'm changing one. We call this the independent variable. Sometimes they call this the manipulated variable. This is the one that I'm interested in changing. So this is the one I have control over. This is on the x-axis. And I'm going to figure out what's happening to the y-axis, what's happening to the other quantity because I'm changing this independent variable. The y quantity is called the dependent variable. Sometimes no relationship is a relationship as well. So you just want to plot the two there. When you get tighter your graph, it should say something like y versus x. So it's like, if you remember our mass and volume experiment, I want to see how the mass of the container changes as I change the volume of solution. So this one will be something like mass versus volume. You can qualify it a little bit more. In the lab we did last year was of 3 different solutions and whatnot, but at the very least you need to show me. I'm plotting the relationship between how might the mass change as the volume is purposely altered. We have some other words here. We talked about outliers as not quite fitting the graph. So if I have an outlier over here, you can just cancel it out. Maybe some group forgot to subtract their beaker and whatnot. 2 fancy words here, interpolation, extrapolation. Both of them sort of looked at patterns. For interpolation, my data set would have been here. I only took data readings at very particular volume readings in this example. I can interpolate, I can predict what I think the in-between values are going to be because I have some lower values, I have some higher values. It is interpolation if I am within my range. Extrapolation is doing something similar. It's saying, based on the trend, based on the pattern that I found, let's pretend that pattern continued onwards. In this case here, it's called extrapolation. And extrapolation, I'm taking that trend there. Usually we can't extrapolate indefinitely, but I'm trying to take the same pattern that I found. I don't actually have other readings out here to test whether I'm correct or not, but assuming the pattern continues, that's what I would imagine new volume would be for this new mass. So random errors we talked about being equal chance of being plus or minus. Random error is tracked in this part of the term. Let's say when I did my Barrett reading, plus or minus, because I have an equal chance being up or down, this part here is random error. This part here will give me some confidence. I thought the Barrett was saying this. Because I have a plus or minus, it gives me a little bit of room to be wrong on either side. Equal chance being a little bit too high, a little bit too low. It's totally possible that something was awry with our actual experiment. Let's say I forgot to subtract the mass of the beaker. when you do your best fit line, it doesn't necessarily have to go through 0, 0. Although you would imagine for a mass volume graph, if I have no liquid, obviously I have no mass. Sure, that can be one single point, but that point is no more important than all the other points that we have. In fact, what's going to happen is once you plot out all your other points, once you do the line of best fit, if you're noticing that you're getting some y-intercept, this y-intercept here is actually an indication of your systematic error. It's actually telling you that when you did your experiment, your procedure, it's possible that all my values have been skewed in one direction, either all too high or all too low. Obviously, we want the y-intercept in this situation to be 0, but if I have a y-intercept, I can actually get a feel of, based on my procedure, how far might I be off from the real value. So in this case here, for example, based on this graph, we have plus or minus, which is a random error. This is equal fluctuation being wrong up or down. But if I forgot to subtract the beakers, then all my values are too high. And in this case here, this is indicative of a systematic error. This is something wrong with our procedure. No matter how many trials that you do, it can't be minimized. You need to fix your procedure. Maybe it's as simple as calibrating your scale. Maybe when you're looking at glass tubes here, maybe you accidentally were looking at the top of the meniscus and all you needed to do was be reminded, oh, we're actually supposed to read the bottom of the meniscus. It can be something as simple as that for a redesign of experiment. When you're doing labs, it's always good not just to say, use better equipment or just too generic, redesign the procedure, but talk about, oh, maybe I forgot to subtract the beakers, maybe I forgot to calibrate the scales, maybe I overshot the endpoint, and try to mention something specific in the redesign of experiment. So those are the two main types of errors. This will mainly show up on your sort of lab, or your labs, your IA and whatnot, but let's say on the IB exam, it's going to show up on your sort of lab analysis, your data analysis section. They're going to give you some sample data, and they may ask you, define these where some places random or systematic error showed up, which one is more prevalent in a particular experiment, and we'll go from there. So. Careful in chemistry, we do use error for this plus or minus, this sort of accuracy argument, how far off I am from the true value, whereas the significant figure stuff we talked about earlier was more precision, was more based on my measuring tool, where are my tick marks, how much detail is the actual apparatus giving me. So those two things are separate, although in physics you do call absolute error sometimes an experimental uncertainty. So that's where it gets a little bit funny. One last note here on error is we can talk about percentage error. This is totally an accuracy argument here. Most people do remember percentage error is going to come out as percent, but unfortunately what they end up doing is they take their measurement value, they take what they thought it was, and they minus off the accepted or the true value. They just get this ratio, forgetting to actually do the difference on top. We're not just comparing your actual number against the real number, we're comparing how far off am I from the true number out of the real number. So on this picture here, my measurement was too big. I'm not taking measurement divided by your true value. So true value, this is measurement. What I'm doing is I'm taking measurement minus the true value. How much range, how far off am I from the true value? Just that difference, and then dividing the true value again, and that gives you your percentage error. Percentage error, you could say just in words, the percentage this percent error too high or too small. So typically we use an absolute value, and that way we don't need to worry about positives and negatives. So hopefully that reminds you of a few concepts for error. You'll need to practice through some of the math of it. Mainly this shows up like I showed you with the titration, making sure you know how to propagate errors through a plus or a minus when you're doing difference in volume. When we do multiply or divide, you just keep the relative error. The relative error increases as opposed to the absolute errors. Lastly here for topic 11 here, we fleshed out a few other definitions. Matter is anything that has mass and volume. Mass is sort of stuff or amount of material, the amount of substance, measured again in grams for chemistry. Volume is that this thing here takes up space. So whether it's solid, liquid, or gas, the amount of space that's taken up will be different. Matter, it has these two properties here. To start organizing matter here, we separate them roughly into things that are pure versus things that are mixtures. Under the pure column here, we have elements and we have compounds. Elements, our periodic table is called the periodic table of elements. So if it shows up on the periodic table, we know right away they're a pure substance. So elements like, oh, carbon is an element or oxygen is an element. Those are pure. A compound it's a little bit strange because a compound actually contains, I have the definition for you here, a compound does contain, compound has two or more different atom types together, right? So think about type when you look at these words here. My compound may be made out of part carbon and part oxygen. It is true, carbon is a different atom than oxygen, but as a compound, because they are combined together, because they always hang out together, they're one group together, as long as inside my container, I just have these blobs of CO2, we are still a pure substance of CO2. Our container is still filled only with CO2 molecules, these CO2 groupings, and they're not a mixture. It only starts becoming a mixture. Let's say I throw some ammonia in there. Remember, there are a few common names I want you to memorize. So ammonia is NH3. This NH3 blob here is not connected to the previously talked about CO2. So in that case there would definitely be a mixture. When we're a mixture, either they mix really well, like gas and gas, so we get a homogeneous mixture like the air. It feels like one material. When I wave my hand in the air, it's not like I feel that, oh, there's an oxygen, or there's a hydrogen, or there's a carbon dioxide. It feels like it's all fully dissolved, versus something that's more heterogeneous, like if you imagine concrete, or you imagine a granola bar, pizza, you see the different bits, and you would assume that they're made out of different parts. So that's how you organize matter. We did a little bit of analysis on things that were not matter. Energy is a good example of it. Energy, although sometimes duality of light, it's easy to think of light as little photons, little packets of energy. It's not matter because it doesn't actually have any substance, any material to it, and it doesn't occupy space. The area that light shines on, you can also occupy that very same space. We start organizing our elements into our periodic table. We'll get into this detail in chapter 3, but we have our periodic table. Roughly speaking, we divide it into two. On the left-hand side, we have our metals. We have our common property for metals here. They tend to be solids in a regular exposure of them, malleable, ductile. We look at the group number, alkali metals, alkaline earth metals. We get less and less metallic as you go to the right. We have our nonmetals. They're typically the opposites, so they show up as gases and liquids at room temperature pressure. They tend to be very brittle, not very good conductors. We have our noble gases. Okay, we have our halogens, and there's this sort of stair step. We would traditionally call these ones here metalloids or semi-metals. They sort of have properties of both metals and nonmetals. So that's roughly how the periodic table is laid out. We'll come back in chapter 3 to look at those periodic trends again. Lastly, for this lesson here is to look at some nomenclature, the fancy name for just naming of chemicals. It's a little bit cumbersome to have to write out the element name all the time. So what we do is we write out chemical formulas. The word formula just means use symbols for the elements. To shorthand it, it also gives you the ratio that your compounds might appear in. Ionic was the harder category to name. Ionic, you can still use the simplification metal, non-metal. We saw in chapter 4, this definition here, we're basically looking at a large EN difference. Usually an EN difference is bigger than 1.8. This 1.8 is a little bit hazy because it really depends on what elements we're talking about. But once that tug of war gets to be very, very uneven, instead of sharing electrons all at once, the electrons end up all going to the more electronegative one. The X gets a full positive charge and the Y gets a full negative charge. So that's what defines you to be ionic. Typically metals are large radius, so they typically lose really badly to the nonmetals. When you do your naming of it, make sure it is metal, non-metal. We change your ending to IDE. When we have multivalent metals, these are typically going to be your transition metals. Transition metals can have multiple charges. So what we're going to do is we're going to add the Roman numeral. Whatever charge, let's say iron is using its 2. This is going to be FeO, iron 2 oxide, or Fe plus 3. We're going to make sure the ratio in the compound, it never is so simple as just one iron with one oxygen. They work out the ratio so that the sum of the charges cancel. Charges are unstable, so if it can, we want to get rid of the charges. Sum of charges is 0. Remember, ionic compounds end up forming that lattice structure, this repeating, alternating pattern. So even though in this case here I'll work on the ratio, it's Fe2O3, that still doesn't mean just 2 Fe's like that and then 3 O's. In fact, that might be one grouping. It's going to be right beside another grouping. It's going to be alternating. On average, every iron has 3 oxygens with it. But in this case here, ionic compounds all form lattice structures. Sometimes they even say crystal lattice because crystal means it's a nice repeating pattern, alternating pattern. In this lattice here, we definitely leave behind little gaps and little holes left over in the structure. Sometimes those holes can be filled up with water, and that's what we refer to as hydrates. So if I took Fe2O3, it's still a solid. I dunk it in water, I give it a soak. It can actually absorb a bunch of water inside the structure. Let's say it absorbs 6 waters here. That means on average, per one Fe2O3 molecule, it's absorbed 6 waters inside. When we do the naming of it, that's the only time we're actually going to use prefixes. We're going to use hexahydrate. There are 6 waters absorbed into the structure. Most important for you to realize is the hydrate is still a solid. It's like a wet sponge. You can still hold on to the sponge itself, although it's a lot heavier because of all the water that's been absorbed inside. We're going to spend another whole chapter on acids and bases. So acids, typically they have something with an H in it. Whether you do the Arrhenius definition or Bronsted-Lowry definition, they're going to be H something. If they're a 2-part acid, they're binary, hydro something acid. If they're polyatomic, if they come from, let's say, carbonate as an example, the ATE ending, we drop the hydro altogether, and now we're going to make it carbonic acid. If it had an IT ending, say nitrite, we're going to then change the ending to nitrous acid. So acids are named a little bit differently. Don't leave it as the ionic name, hydrogen nitrite, hydrogen carbonate. You do want to convert it over to the acid name. This is where you need to memorize the polyatomics on that green chart there, so make sure you have those down. I also included bases for you. No real surprise in the naming of them. They're going to be something hydroxide. We saw in the acid-base definition, that was just the Arrhenius definition. They're supposedly holding on to OH so they can release them when you drop them in solution. That was all the detail for sort of ionic compounds. Covalent compounds are going to be non-metal, non-metal. We don't have as many non-metals, so the variety is a little bit different. But in this case here for non-metal, non-metal, because we end up sharing electrons, we end up getting many different combinations. So carbon dioxide can be a triple bond in between them. It can be a carbon double-double, so carbon dioxide. It's the same 2 elements. And our wording of it here is we use the prefixes to show exactly how many there are. So this one here would be carbon monoxide. If the first one happens to be mono, you can drop the mono. So carbon monoxide or monoxide. In this case here is carbon dioxide. That was sort of the naming of compounds, ionic and covalent. Then we looked at different types of reactions. For our 6 common types of reactions, make sure you can classify the different types. Synthesis is it smushing together. Decomposition is the opposite, it falls apart. Combustion is always easy to recognize, very, very exothermic, very, very easy to release energy to the environment. 3 out of the 4 things are stuck in place. We're going to always assume for a combustion, the complete combustion. For a complete combustion, we're going to fully get CO2 and water. Here's a nice hint if you get a multiple choice question here. What if I had incomplete combustion? Incomplete combustion meaning you don't have that much oxygen. There's limited oxygen to actually burn with your fuel. Instead of getting the full CO2, we end up balancing getting off C's and some COs. COs is a toxic gas, so you want to be really careful with that. Carbon is going to appear as soot, so it's going to make a very dirty, very powdery flame for you. Single replacement here, we talked about activity. We'll see this a little more in redox as well. If A is more active, depending on A being a metal or non-metal, if A is a metal, metal is going to fight against metal. If A is a non-metal, non-metal is going to fight against non-metal. And to end off here, we have double replacement here. I want to do one example of double replacement just to qualify a little bit here. I think we did this on one of our labs. We took lead nitrate, PbNO3 and Ki. Remember in this section here, they give us 3 keywords. They ask us predict, see if you can guess what the products are. We're going to classify which of those 6 types of reactions. They're not the only types, but those are the easiest 6 types. And then we're going to balance to make sure mass is conserved, make sure all the atoms are accounted for. In this case here, we see it's compound and compound, metal, non-metal, metal, non-metal. So we don't need to check the solubility. We don't need to check the activity series. We know they're going to switch charge, partners. So Pb and I, K is going to be NO3. As a general rule, these numbers don't drag over. So it was NO3 here. It's not NO3 here. Do yourself a favor and actually check what the right compound should be. K is an alkali metal +1, nitrate is a -1. That confirms I don't need this bracket or anything like that. Once you have the ratio, don't write the charges anymore. Pb is one of those multivalent guys. Pb can either be +4 or +2. At this point here, we're guessing, so you wouldn't be wrong if you put lead 4 iodide here, but seeing as lead is already using as lead 2, I know that because nitrate is -1, let's use lead 2 here, so PbI2. Once you have written the correct compounds, we can balance it. Should be 1, 2, 1, 2. We didn't need to check the activity series because I know it always gives you the same chemicals anyways, the same combinations. This one here is referred to as your balance equation, or your chemical equation, fine. For this double replacement reaction, we can do in a little more detail. All double replacements always make it look like we create 2 new things. What I want you to do is I want you to check that pink solubility chart. In this case here, because it's a little bit hard to mix a powder and a powder together, usually what we do is we dissolve this guy and we dissolve the Ki. Because the ions are fully dissociated, we then mix them together and see whether they've actually formed a compound. If you remember your solubility chart here, we start off looking at the negatives first. We're going to find nitrate fairly high up. It's actually going from sort of most soluble at the top and less soluble. The nice thing about nitrate is nitrate with any positive is said to be soluble. These ones here dissolve very well. We're going to put AQ for them. So this one is aqueous. This one here is aqueous. That's something nice to memorize. The other ones that are nice to memorize, these top 3 rows can be summarized. Any alkalis, any H pluses, or even ammonium compounds with any nonmetals are similarly soluble. So I didn't even need to check this one here. This is an alkali salt, soluble, aqueous. Ki, soluble, aqueous. Remember, aqueous means that they're fully dissociated, they're broken apart. That means they're not holding hands anymore. What we have, even though we've labeled the bottle PbNO3 we just have plain old Pb ions, plain old nitrate ions. Ki is also aqueous, K plus, I minus. The only one in this example that's a solid is actually this one. When you check iodide, iodide for sure is going to be soluble with some things, but we're going to find lead actually is underneath here, and that one there is actually low soluble. If something is low soluble, it's solid. So out of all these ones here, that one is a solid. To get the detail of this one here, we can write what's called a complete ionic equation. Complete ionic equation involves break up any aqueous salts because they aren't holding hands, but we're going to leave any solids. So just to finish off here, we have, in this case here, PbNO3 That means we have Pb ions, we have 2 nitrate ions, 2 potassium ions, 2 iodide ions. This PbI2 is a solid, so I'm going to leave it together. They have actually bonded together. They've made a new compound. Even though this looks like I created KNO3, it's actually just 2K plus and 2NO3 minus. You'll notice in a dissociation reaction, the polyatomic groupings still stay together. They're covalently bonded inside. Water can't chop them apart. That's your complete ionic equation. For a properly worded question, the reactant side should all be aqueous because that makes it easy to mix. On the product side, all bets are off. You could get no solids. You can get one solid like in this case. In this case, because a solid comes out of a fully mixed solution, we're going to call this solid here a precipitate. A precipitate is a solid that forms, it crashes out of solution. And what we're going to do in this situation, if I'm seeing chemicals that appear the same on both sides, we need to cancel those before we get what's called the net ionic equation. Let's cancel out the spectators. Just like spectators at a hockey game, they just watch the game, they don't actually participate. So I notice that I have 2K plus before, 2K plus afterwards. That's a spectator. Didn't do anything, didn't change. 2 nitrate similarly didn't change, cancels out. So really, once I cancel out those spectators, those guys just come along for the ride. The real equation in this double replacement is the lead from the first solution found 2 iodides from the second solution. They realize they shouldn't be bonded together, and they actually solidify out and they crash out of solution. They form that precipitate afterwards. We did this on our KSP lab here. We saw this actually formed a yellow precipitate, so we can actually predict the identity of this PbI2. So only for a double replacement reaction, they might get you to think a little bit about solubility so that we can go through complete ionic and figure out, did I really create 2 new things? In this case, we say, nope, we only created this 1 new precipitate. Even though KNO3 looks like it's bonded together, this one similarly is aqueous. That one is just swimming around potassium and nitrate just like it was to begin with. So hopefully that reviews some things from way back in Chemistry 11 here, just reviewing measurement. We'll pick it up from moles for tomorrow. Thanks, guys.